liquid crystals. So I want to ask some questions. There are various order parameters that are used to describe liquid crystals. The directors, Q tensors, I'll say something about this. So usually these are, well, some of them, the director is allowed to have sort of point and line singularities, but I want to ask whether it's relevant that they could, you know, for the physical reasons or mathematical reasons, to allow them to jump across surfaces. Okay. And related to that is that some of the theories, like the Ozone Frank theory, give infinite energy to defects that you actually see. So I want to ask whether there's some way of fixing that while keeping a director theory. Okay. And thirdly, a sort of general issue about what role does a function space play in mathematical models and where does it come from and stuff like that. Okay. So here's a very quick summary of classical models of pneumatics and cholesterics. So these are all going to be static models for a liquid crystal at a constant temperature filling some bounded region omega, described in terms of their corresponding free energy functionals. So here's a typical sort of caricature of a pneumatic liquid crystal, sort of rod-like molecules with a mean sort of orientation in the direction of a vector field n. And so that's the order parameter for the Ozone Frank theory. So it's a two-dimensional order parameter because it's a unit vector. And so the energy is you integrate a free energy density that depends n and on the gradient of n. Now in this subject, it's always a nabla instead of a d. So I've changed from d to a nabla here. Okay. So for the Ozone Frank energy, it depends on n and the gradient of n. All the terms are okay. So there's an issue. There's also cholesteric liquid crystals. Cholesterics have some chiral nature to them. So so if you've got a cholesteric, you add this t term in here. That's just a real number. So otherwise, it's quadratic in the gradient of n. There's n that appears here. There's n that appears here. There's 4 elastic constants, 5 if you have got a cholesteric, and they usually satisfy some inequalities to make this a positive quantity. The last term here is a null Lagrangian, so it's Euler-Lagrange equation. That doesn't contribute to the Euler-Lagrange equations, only to surface terms. Okay, so now you notice that did that click? That single arrow turned into a double arrow, and that's because really that arrow doesn't mean anything. Statistically, the molecules are the same in one direction as in the opposite direction. So that's a slight worry, which I'll come to later. Okay, in the Ericsson theory, you add another variable s, which is a scalar that is supposed to give you the degree of order. So s equals 1 would be perfectly oriented molecules. S equals 0 is completely disoriented molecules. So now you've got a 3-dimensional order parameter, and the energy functional is allowed to depend also on s and the gradient of s. And then most popular among physicists is the Landau-de Gennes theory. Now here the order parameter is a matrix Q of x, and this matrix at the point x is a normalized second moment of the probability distribution for the molecular orientations at the point x. So this is so P denotes the orientation. It belongs to S2, the unit sphere. This is a probability distribution, so it's non-negative. It's symmetric. That's because of this head-to-tail symmetry. Integrates up to 1, of course. This is just subtracted off, so the trace of Q is 1. Okay, so you can take the trace inside, the trace of that is 1, the trace of that is 1. So the trace of Q is 0. Q is obviously symmetric. Another point is that Q plus 1/3 the identity is a non-negative matrix. Usually you assume it's strictly positive. That means that its minimum eigenvalue should be bigger than minus 1/3. Okay, so now you've got a 5-dimensional order parameter, okay, because it's symmetric matrix, which is trace free. The energy is supposed to be given by integrating some free energy density depending on Q and its gradient. And it's conventional to split this into 2 pieces. First you put the gradient of Q equals 0. That gives you something that just depends on Q. And then you subtract it off again, and that gives you this, which really depends on the gradient of Q. Okay? This is called the bulk energy. This is called the elastic energy. In 95% of papers, the bulk energy is taken to be this quartic form here. Usually A just depends on the temperature. Usually it's linear in the temperature, and B and C are taken to be constants. However, if you take that bulk energy, there's nothing in the theory that will preserve the eigenvalue constraint. So a good thing to do is to have a bulk energy that blows up as the minimum eigenvalue goes to minus 1/3. And that was proposed by Catriel and Sluckin, and I can't remember all the authors, and later by Apala Majumdar and myself, on the basis of a derivation from a more microscopic theory, the Onsager theory. Now, as for the elastic energy, well, typically it's typically assumed to be, again in the pneumatic case, quadratic in the gradient of Q. There's lots of terms you could have here. It's kind of convenient to take 4 of them in the pneumatic case, for reasons I'll say in a moment. So the first 3 are purely quadratic functions of the gradient of Q. The 4th one has a Q out the front, but is still quadratic in the gradient of Q. And if you're doing cholesterics, you have this term which is linear in the gradient of Q. And this epsilon is there, sort of gives the chiral nature, if you like. And how do you go from one theory to the other? Well, if you make this ansatz that Q is uniaxial, so it has this form for a constant S, n being a unit vector, and you just take that and you shove it into here, and you formally calculate the gradient and everything. That means you'll get sort of, things like n tends to the gradient of n and things like that. Okay, so then you end up with the Ozone Frank theory. And the fact that you've chosen to take 4 constants here in the pneumatic case, that there's an invertible matrix, 4x4 matrix that takes you from these Li to the 4 Frank constants, K1, K2, K3, and K4. And then if you want to get the Ericsson theory, you let S be a function that depends on, you allow S to depend on X, and then that will go from this theory to the Ericsson theory. So those are the sort of classical models. They're not the only models, but they're the classical models. So now I wanted to say something about smectics, well, particularly because they were talked about earlier in the meeting, it seems I'm graduating. I started trying to do pneumatics, and then a little bit of cholesterics, and now I'm getting onto smectics. So maybe soon I'll do dynamics. I don't know. Anyway, so smectics are interesting. They're a phase, and this is smectic A. So you get layers which are approximately 1 molecule thick. Actually, the average is about 1.4 molecular lengths. So molecules are about sort of 2 nanometers long or something like that. And the molecules more or less point normal to the planes. Right? In smectic A, they're tilted with respect to the planes. In smectic C, sorry, in smectic A they're like this. In smectic C, they're tilted with respect to the planes. So There's lots of different models for smectics, which makes it very confusing. Probably when I finish, it will be even more confusing. But so it seems to me that there are two kinds of models, and the first assumes that each layer has a constant thickness. Okay, and so that means that at a sort of continuum level, at each point you have a director, but you also have a normal to a layer. We're thinking that the layers are extremely thin, so we can sort of at a continuum level assume we've got a director and a normal. And the normal I'm going to call A of x. It's a unit vector. So the claim is that if A is sufficiently smooth, then the curl of A is 0. All right. So there's an argument given with sort of line integrals and stuff in the literature. Here's a different argument. So it must be true when there are two arguments, I guess. So. Okay, so here's a different argument. So suppose that x is 0 and that the normal at 0 is E3. So the layer surface through x, through 0 that is, has the equation x3 equals f of x1, x2, with the gradient of f being 0. So that means that the normals to the surface, to the layer through 0 at near 0 simply cover a neighborhood of 0. So it looks a bit like that. Okay, so here's 0, here's layers, and the A of 0 is E3. Okay. Right, now on the surface, for x on the surface, A of x is given by, this is on the surface through 0, the layer through 0 is given by this. That's just the usual formula. And you start with supposing f is smooth, and you start computing the derivatives, and you find that these various derivatives are 0. And so the curl of A at 0 is therefore given by this expression. And I claim that that is 0 because A of 0, 0, x3 is in fact E3. So now that's of course true at the origin. Why is it true further up? Well, I mean, if you take any point on these layers, the nearest point is given by the line giving the nearest point is the normal at this point. So somehow you argue that well, if this wasn't the nearest point, you could sort of go down like this. And so there's a little argument that shows that in fact everything on this line is the normal to all the layers through this point. And so you get that the curl is 0. So, okay, so that means now for smectic A, you could take n to be A, right? Because the normals to the layers are, the director is normal to the layers. So that means since curl of let's go back to the Ozone Frank formula somewhere. So there we go. So if now we're taking t equals 0, we're taking t equals 0, and so now in the Ozone Frank formula, you would have the curl terms would go away, and this term goes away. Does that term go away as well, or do you just set it to 0? I'm not sure. I think that term goes away as well, and so you end up with the first term, which is the integral of k1 divergence of n squared, and so setting k2, you do set k2 plus k4 equals 0. That's right. And so now you've got to minimize this subject to the curl of n is 0 and n is a unit vector. Okay, so that's the sort of most primitive model of smectics. Now, if omega was simply connected, that would mean that n was the gradient of some phi, and then you'd have to minimize the integral of Laplacian phi squared, subject to the iconal equation that the gradient of phi had unit length. So that does have some solutions. For example, if n minimizes the integral of gradient n squared and n is the gradient of phi, then that of course will be a minimizer. So for example, x over norm x would be some minimizer to this problem for some boundary data. But you see that the problem of boundary data is a bit awkward. You don't want to, I mean, what are you going to, you'd like to be able to specify somehow n on the boundary, and that's not going to really be easy. Now, so now there's a famous functional, the Avilas-Giger functional, which is quite similar. So now instead of so you could imagine if you had if you had a big constant out the front here, that would be more or less the same problem, right? So what's the? So it's always said that this is a model for Smectic. So I went away to look at the paper, and here's what they say in the paper about the derivation. Okay, complete with misprints. This is absolutely accurate how it's written. Simple examples and physical considerations, Ericsson 17 and Sethner 18, suggest that the solution of the following relaxation problem explain with accuracy the phenomena. And then you look at Ericsson 17 and Sethner 18, and they both say private communication. So I'm not sure really whether there is a sort of derivation or not. Okay, anyway. Now, so you could do something a bit different, and this is done in the literature. So a more general model would be to minimize some integral of w of n and a, and the gradient of n and the gradient of a, and such a model was proposed by these people for Smectic C, and they imposed the constraint that a dot n was cos theta. Theta was the angle for the of inclination for the. So it could have been pi by 2, for example, if you'd wanted to do Smectic A. Again, you have a bit of a problem with the boundary data, I think. So I mean, so you could, for example, add a term like this and impose boundary conditions just on n. That would be a kind of reasonable thing to do. So I think that's an interesting kind of model. But I've not tried to study it, but they do. I mean, they do a lot of studies of this kind of model. And then there are models that allow variable layer thickness and dislocations and so on. So here's a sort of some kind of micrograph of where you see a dislocation in the layers. Okay, so that sort of thing does happen, and they typically introduce a molecular number density m of x as a new variable, and the Smectic layers are seen as sort of density waves in this variable. Now, in the de Gennes approach and that of Chen-Lubensky, it's assumed that you have some sort of base density rho 0, and that m of x is a perturbation of that rho 0 plus rho of x, and that rho of x is given by some amplitude times cos of phi of x. And rho 0 is supposed to be a constant average density, and then they form this complex order parameter. So the rho of x describes the fluctuations in the density due to the Smectic layers, and the gradient of phi then gives the normals to the layers. So I get so worried by this, how we're supposed to, I mean, m of x is supposed to be a macroscopic quantity, right? But in order to see the layers, it's supposed to vary over distances of the order of a molecular length. So how can one sort of rationalize that? So here are some sort of random thoughts in various directions. So this is related to the interpretation of the probability distribution of molecular orientations and how that can be thought of as a macroscopic variable. So first of all, let's fix it. This is how I've always explained it in numerous lectures over the last 7 or 8 years, but now I have serious doubts about it actually. But anyway, first time, okay, and a point x, okay, and then look at some tiny little ball around x of radius delta, which we're going to use to coarse grain the system. Okay, so now in the ball so that's this blown up, and in this ball you've got lots of molecules. So you're going to choose delta to be sufficiently small so that effectively you can consider this as a macroscopic point, but on the other hand, sufficiently large to have enough molecules so you can take some kind of average over that ball, right? So then you start picking points at random from that ball and looking to see what the orientation is. Okay, so there we are. That's what I just said. Now, suppose, just to give an idea of the order of magnitude, suppose you take the molecule to be a circular cylinder of length d and radius a, and assume that the molecules fill a fraction theta of bx delta. Then the number of molecules in bx delta is that expression 4/3 pi delta cubed theta over pi a squared d. And if you set theta as a half, so you suppose the molecules more or less fill half the space, say, A is d over 4, that's so that it's a fairly thin cylinder, I suppose. D is about 3 nanometers, that's more or less what it is. So that number is 1 billion for delta being 1,000th of a millimeter. Okay, so lots and lots, so large numbers, right? And it would still be 100 if delta was 10 nanometers. So 10 nanometers is 5 molecular lengths. 100 would certainly be enough to get some kind of approximation, you would think, right? But it's not. But that's not going to get us down to something that varies over molecular lengths, right? But maybe the solution is that you should also average over a macroscopically small time interval. I mean, this is soft matter, and the molecules are jiggling around, you know, and the orientations, they may be moving up a bit. So maybe then you could reduce delta, perhaps to a nanometer, say. So, I mean, there's all sorts of issues here, and I've never seen them sort of discussed in any rational way, but they would certainly be essential if you were going to do some rigorous derivation of a continuum theory from a molecular one. So first of all, I mean, if you've got a really small radius, then the molecules will typically overlap the boundary. Okay, so you just choose the proportion of the molecule that's inside your little ball, maybe. Okay, that would be okay. There's how much they're jiggling around. There's whether you want to do this, whether you want to have a dynamical theory, because then, you know, the time scale, the time interval over which you're averaging, it better be much shorter than the sort of typical time scale that you're interested in. It has a kind of flavor of ergodicity in the sense that you're trying to replace maybe a spatial average with a time average. But on the other hand, it's not a sort of isolated system. It's, you know, it's a little part of a bigger system. So it's anyway. Okay, so these are sorts of things I'm thinking. So here's a sort of remark, which again I don't know quite what to make of. And the first time I did it, I made a blunder. So I'm rectifying the blunder now. So suppose that you thought of these as being the molecules, all right? So and this is, say, gaps between them, for example, this is the sort of characteristic function, if you like, of the molecules. Now, suppose that. So one way you might think of getting out of this problem is that you might average over a sufficiently large ball, but the center of the ball can vary. Right? So maybe if you average over some ball which is large enough to contain lots of molecules, that average is meaningful macroscopically because you've averaged over a large enough ball, but maybe it could vary microscopically, you know, because you're moving the center of the ball. So here's a sort of test. I mean, so if g of x1 was, say, L periodic, and you averaged over some cube of side KL, exactly, k times an integer times the period, then the average is constant. So it gives you no information, actually, at all. It doesn't matter where x is, it won't give you any information. And the same thing happens if you can average over a ball, which is sort of interesting. Again, if you average over a ball and you take, say, sine kx1, okay, then there are certain values of k given by the roots of this, if k delta is the root of this equation. such that the integral over any ball is the same. Okay, so it's like a kind of, so this is related to something which is called the Pompeiu problem. And the Pompeiu problem is you have, say, an L infinity function defined on R3, and you take an object, which could be a ball or a cube or parallel pipe or whatever. And what the game is, you're given the integrals of this function over any rigid translation and rotation of this object. And and you're told, for example, that the integrals are all 0. Does that imply that the function is 0? Okay, and it's not true for a ball, and that's one. This is a counterexample here, but it is true for cubes. You see, when I did the first calculation, I just took a cube oriented in a particular way. If I was allowed to turn the cube, I get more information. You don't get any more information from turning a ball. Okay, so I don't know whether this has anything to do with Smectics, but anyway, it's interesting. I plan to pursue it a bit. Okay, so now an example of a free energy function defined in terms of n and phi is that proposed by Kleiman and Parodi. It's given by this expression. You've got your favorite W here from Ozone Frank, and then you add on a term with n and the gradient of phi here. Okay, so and then Weinan and later Santangelo and Camion argue that a good approximation is given by this expression, together with the constraint that n is the gradient of phi over the absolute value of the gradient of phi. Well, it's kind of interesting. For this model, it's easy to prove the existence of minimizers. For this problem, I've no idea how you do it. Okay. So models using the density rho rather than phi. So that's the Chinese model of Pingwang Zhang's group and so on, which is rationally derived. But as you see, it's not exactly. It's got lots of variables. So they have fourth moments as well as. So the C is the rho. And they've got myriads of terms here, but it's rationally derived on the basis of a more microscopic theory. So this is a recent model, which is a good deal simpler to look at anyway, where you have an n. So this is the simplest possible form of it is taken there, and this term enforces oscillations of rho essentially in the direction of n. Okay, and this is some other term. So, all right. So those are models of Smectics. Okay. Now, So I think that you learn things from solid mechanics for liquid crystals. So, as we've seen, it has a similar variational structure. It's an integral of the gradient of a vector, the energy, and minimizers can have singularities. Well, we've certainly seen that. We've seen singularities in which the gradient jumps across planes, for twins, for example. And the predictions of the model depend on the function space. Now, we haven't seen that, so here's an example. So his example is cavitation. So here's an energy functional, which is not such a bad caricature of an energy functional for rubber. H is a convex function that has a very sharp minimum, say, around delta equals 1, because rubber is almost incompressible. And so you take the ball, center 0, radius 1, you try and minimize this subject to y of x is lambda x on the boundary. Okay, now, so that means you take this ball and you pull out on it uniformly on the boundary by a factor lambda. And it's a theorem that the minimizer among smooth functions y is in fact lambda x, and that's because this is a polyconvex function and therefore quasi-convex, and that's the definition of quasi-convexity. Right? But among radial deformations, at least in W12, the minimizer for large enough lambda satisfies R of 0 is bigger than 0. It wants to cavitate and form a hole at the origin, and so that's an example of the Lagrangian phenomenon. We have the same functional, but its infimum and the minimizers are different in different function spaces. So that's what the minimizer looks like. And that's really what happens. It's a classical failure mechanism for polymers. So you might say, oh, well, that's okay, W12, that looks then a good space to have used because it would at least have given this phenomenon. But is it the largest such function space? And the answer is no, because the body could develop fracture surfaces across which Y is discontinuous, which can't happen in any Sobolev space. So it could develop a crack like that, for example. And then there's a theory, the Frank-Four-Marigot theory of fracture, in which you suppose that Y is in SBV, special functions of boundary variation, which have a jump set, a well-defined jump set, and then you should really add in the simplest case, a factor times the area of that jump set. Okay, so then you have different function spaces, and you get different answers. So that's the important conclusion to draw for liquid crystals, that the function space is part of the model, and the proof is that if you change the function space, the predictions change. Okay. And the Lavoisier phenomenon occurs in the Ozone Frank theory. So, for example, if you take the one constant case here and you minimize subject to n of on the boundary of the unit ball is x, then if the space is C1, well, there aren't any unit vector fields that are C1 that match that on the boundary, that sort of topology. And so, if you like, the energy is infinite for them, but you can take n of x is equal to x over norm x, which in fact minimizes this under certain circumstances. Okay, so well, it minimizes it subject to its own boundary data. So if you think that's cheating the plus infinity there, then there's another example of Hart and Lin where you have smooth degree 0 boundary data for which both infima are finite, but that in W12 is lower. Okay. So now I've already touched on the description of defects. So let's consider the Ozone Frank theory for pneumatics. So there's the energy again. Then it's obviously bounded above by a constant times the gradient of n squared. And then if you make these assumptions, so-called Eriksson inequalities, then it's also bounded below by some other constant, positive constant. So a natural function space for this would be, you think, W12. That's what everybody would use with values in S2. And the Euler-Lagrange equation has solutions that represent point defects, like this hedgehog, it looks like that. And if you make this one constant approximation, which I just did, that K1, K2, K3 is K, K4 is 0, then in fact this is the unique minimizer subject to its own boundary data. And in this case, as we've already seen in this meeting, any minimizer is smooth, except for a finite number of point defects at points xi, and near each of those defects it looks like a hedgehog, except that you have to have a rotation out the front. And this sort of thing, by the way, is not known. I mean, a lot of stuff in liquid crystals is not known if you don't make this assumption. And in particular, you don't know that you just have a finite number of point defects. So disclinations, so that's the same thing, except that now the director points radially outwards from the generator of a cylinder. So now you have, that's n hat, it looks like this is now the two-dimensional radius, and so that's what the gradient of n squared is, and that, you see, is only in W1p if p is strictly less than 2. Okay, so it's not in W12. In other words, this defect, which you do see sometimes, has infinite energy according to the Ozone Frank theory. And then that was a bit far, so it's infinite energy. Okay, so and then there's index 1/2 singularities, which we already saw. So here the director is supposed to be it has 0 component into the screen, and it's parallel to each of these indicated lines, and that's another index 1/2 singularity. And these also they're not in W12, and Okay, so there's a problem here about orientability, which I think I'll talk about later. But even if, but in any case, you can't describe these by n being in W12. Okay. Now, that these defects have infinite energy obviously arises from the fact that W grows quadratically in the gradient of n. But there's probably no reason to suppose it does grow quadratically in the gradient of n. I mean, when you have quadratic functions, that's because you've taken some expansion and said that the gradient of n is small. But if you're at a defect, the gradient of n is infinite, right? So why? I mean, so there's no reason really to suppose that. So a possible remedy would be to change W and make sure that it had subquadratic growth at infinity. Okay, and that wouldn't, you could do that without violating all of the things that you like about the Frank constants and so on. So this is an entirely artificial way of doing it. Here's your favorite W, the actual Ozone Frank one, and this is a perturbation of it that tends to it as this parameter alpha goes to 0 and has subquadratic growth. Okay, so if you took alpha as small as you like, you would not be able to violate any inequality that you met. Okay, so this is not physical or something, but it just shows that in principle you could do it without violating anything. And also, it would be convex and everything like that. So here's another problem: boundary conditions. Suppose if you have a domain with smooth boundary and a sufficiently smooth unit vector field is given on the boundary, then it's known that there's a unit vector field in W12 that matches it, right? But if you have a cube and n is the inward normal to the boundary, then my student Stephen Bedford showed that there isn't such an n. So thus the Ozone Frank theory doesn't apply to homeotropic boundary conditions on a cube. And yet that's the sort of domain which you actually use for liquid crystals. Liquid crystal cells tend to have things like that, corners. So a theory with subquadratic growth would be okay. Now the index 1/2 singularities can't be modeled that way because they're not orientable. So they can't be described by they can be described by a line field, but not by a vector field. So here you see the problem about. So if you imagine that you have this double-headed arrow that's parallel to this. Now if you try to orient it, well, you have to make some kind of choice, and then it means you go up here, and that means you're going up here, but that means you're going down here, so you've got a kind of contradiction in this region, so you can't orient it. And the same thing arises for smooth line fields in non-simply connected regions. Okay, so that casts into doubt the derivation of the Ozone Frank theory from the Landau-de Gennes one, in particular, if you're working in a non-simply connected region. But you could handle it by allowing n to jump by 180 degrees over suitable surfaces. Okay, so that's a purely mathematical reason why it might be useful to allow n to jump across the surface. Just a remark that if you have a W12 line field in a simply connected region, it's orientable, but this is not a W12 line field. So Stephen Bedford, who's a very, very good student, but left mathematics to go and work on computer games just recently. He proved, really good, excellent thesis. This is one of the things in his thesis. He did a lifting theorem for this. So if you have if you know that n tends to n is in W12, then you can always find an SBV function such that that it gives the same line field, and m plus is equal to minus m minus across any jump. So this applies to the second situation of the being outside a cylinder, but not to index 1/2 defects, for which you'd have to extend this to W1p for p less than 2. And he has similar results for the Ericsson model. So now the Landau-de Gennes theory, the description of defects there is going to be different because the Euler-Lagrange equations are elliptic. So there is a slight problem if you use the bulk potential, which blows up as the minimum eigenvalue goes to -1/3. But at least in one case, you can still get the Euler-Lagrange equation. So the defects in general are not described by singularities of Q, but rather by regions where the gradient of Q is very high, where you might not be able to choose, make a continuous choice of the eigenvectors for the gradient of for the eigenvectors for Q, not the gradient of Q. Yeah. Now the situation might be different if you had an energy which was not convex in the gradient of Q. Which is convex but not quadratic in the gradient of Q. And it's interesting that a famous counterexample, a spheric and yarn, for irregular minimizers is actually exactly in the framework of the Q-tensor theory. So, but it has a, you see it has an S of X here, if you like, that is mod X. So it's possible that for some versions of the Q-tensor theory you would have singular Qs. I'm not sure. Okay, now planar defects. So let's explore whether it might be reasonable to consider a free discontinuity model for liquid crystals. So here's your favorite, either Ozone Frank, or maybe you've modified it to be subquadratic for large gradient of n. But now you're going to work in SPV. And that means that you have a well-defined jump set, which has a well-defined normal, nu, and well-defined limits. So you're going to add some term that gives you the energy over the jump set. So what would that energy have to be like? Well, it should be frame indifferent. So if you pre-multiply by any rotation, you should get the same thing. And it should be invariant to reversing the sign of n plus and n minus, because the signs don't mean anything. And so if you analyze that, you find that, in fact, f should depend on these three vectors through four quantities: the squares of the inner products and the product of the inner products. And you can actually say what the domain of that function is. Okay, so what are possible candidates for planar defects? So the first is, I think, pneumatic elastomers. I've not really worked through this, but you see, so pneumatic elastomers are a mixture of elasticity with liquid crystals. So they're polymers to which liquid crystal molecules are attached. And they behave very much like martensite. So you get these layered configurations. So the energy functional is usually taken to be this, so quadratic in the gradient of y, and then you've got this tensor here, which depends on the n. So we've got y, so I depends on y and n, and it's assumed incompressible, so that y is subjected to determinant gradient y is 1. And then if you minimize the integrand, you see there's no gradient of n in this. So that means you can minimize out the n pointwise. If you do that, you get some functional integral of w of the gradient of y, where w turns out to be this. It doesn't matter what the form is. But what's really important is that it's not a quasi-convex function. And that's why you get the layers. Okay? Well, since we know that the gradient of y is going to jump across these planar interfaces, that suggests that the minimizing n would also jump across those interfaces to a good approximation. So maybe it would be a good idea to look for solutions here in SPV. The second example is order reconstruction. So this is a classical problem that's being considered by many people. It's a bit more of a theoretical problem than an experimental one, but there are some experiments. So the idea is you take two plates, and the liquid crystal fills the region between the two plates. They're parallel plates, but they're a very small distance apart, delta. and you impose antagonistic boundary conditions on the two plates. So at the bottom, the n has got to be in the x1 direction, and on the top in the E3 direction, x3 direction. So you can use this, analyze this using Landau-de Gennes. Maybe since we want to end on time, I won't say more. Let me just get to the conclusion. You do some rescaling, etc., and then what do you get? Okay, so the conclusion is that under some assumptions, the Q tensor will vary linearly across the region between the plates. And that means that the director, which is typically identified to be the unit vector corresponding, the eigenvector corresponding to the largest eigenvalue, actually is E1 up to some point, well, okay, S1 and S2, let's take them to be equal. So this would be a half delta. So up to halfway, it would be E1, which is the boundary condition on the bottom plate, and after that, it's E3. So that the director has a discontinuity on the plane x3 equals delta over 2. Now it's interesting that Claudio Zanoni's group has done molecular dynamics simulations on more or less this situation. So here we see the horizontal axis is the thickness across the plate. And these graphs here show the various components of the Q tensor, which were calculated, using molecular dynamics. And if you calculate the eigenvalues, you see that indeed they do cross at some point in between. So it's some kind of verification that it's not such a bad model. However, let's see whether you could model this using a director theory and SPV and so on. So here's an attempt at doing that. So we take the one constant case to make life easy. And here's the form for the integral over the jump set. So you see it's going to be, this will be 0 if n plus is plus or minus n minus, which is what you want. R is less than 1. I want to minimize this subject to n being plus or minus E1 on the bottom and plus or minus E3 on the top. So you formally can get that from this Landau-de Gennes functional here, subject to this uniaxial constraint. So what I'm going to say in a moment, I'm going to express things in terms of Q, but you've got to remember that it's secretly really just n and the gradient of n because we're using this constraint. Okay, so there are two candidates for minimizers, which are the ones corresponding to the Ozone Frank theory. So what happens is one of them, it's horizontal on the bottom, and as you go up it twists to become vertical, and on the other one it twists the other way. Okay? So you get two of these, and that's what they are expressed in terms of Q. It doesn't matter what the formulae are. So what you could prove is that the problem has exactly one minimizer. Just try. The problem has a minimizer for any delta, and we believe that that there's a critical delta, so that if delta is bigger than this delta 0, then those solutions are the only minimizers, whereas if delta is less than delta 0, then any minimizer has a single jump with a jump set which is located at some value of x3, which actually can be arbitrary. In fact, according to this model, we think. Okay, so why does it want to have a jump in this model? Well, that you can easily see because for the Ozone Frank, for any smooth solution, you would need to go from horizontal to vertical in a distance delta. So the gradient is of order 1 over delta. So the square of the gradient is of order 1 over delta squared. Now you integrate over the thickness, so that means you multiply by delta. So the energy of those solutions is of order 1 over delta. But you can make this competitor, basically you have E1 up to halfway and then E3. You get 0, and the elastic terms are 0 for that, and you only pay an amount for the surface jump, which is fine. So if delta is small enough, it must be better to do that. Okay, so that's why you need why you need a... okay, so that's that. I went to talk about the related problems about cholesterics, which, okay, very good. So now, finally, Smectic thin films. So this was a picture I showed right at the beginning. So, and this is what actually gave me a bit of confidence that this is not such a stupid thing to do. So these are pictures from Emmanuel Leclase's group. So these are the Smectic layers. This is what they believed at that time. They now believe slightly different. I'll show you. Was the configuration of the layers, and each of these is one of these pointed sort of into the screen, if you like. So and so you see that these are Smectic A, and so if you believe that the molecules are perpendicular to the layers, since the layers have a discontinuity in slope at these red lines, for example, so will the N. Okay, well, you can. We've not done very much on this, but we're hoping to do more, and maybe we'll use a different model from this one. But this is an SPV model, which is a modification of the one I showed due to Pevney, Selinger, and Sluckin, for which at least you can prove the existence of minimizers in SPV. Doesn't really matter. Okay, so now, so this is the last slide. So, so this is their latest. It's very difficult experimentally to be absolutely sure, but this is their latest belief for what the layers actually do. So if the thickness of the film is fairly low, then so on the bottom the molecules are supposed to lie horizontally. Okay, so you see that the Smectic layers here are horizontal. So there's a real jump, if you like, in the director along here, for which you'll pay a lot of energy, whereas here it won't be so bad. So that's for thin films. For slightly thicker ones, it will match the boundary data. So the layers are vertical here, therefore at the bottom the molecules are horizontal, but nevertheless you have another discontinuity here. So this is what they think are the solutions, and so we're working on that, and there are ongoing computations of a former postdoc, Andres Leon Baldelli. So we hope to. I think some of the simpler models might be good actually for discussing this. Okay, that's it, and I stopped with 1.5 minutes to spare. No.